Okay, section 11.4. Determine whether the following situation is a permutation problem or a combination problem. Okay, a locker contains 10 books. You select 2 at random. Do you care which order the books are selected in? Nope. I don't care which one's first and which one's second. This must be a combination. So remember that. It's a group of 2 books. Order is not significant at all. Just a group. They didn't ask me to calculate anything. They just wanted to know if I understood the situation. Oops. Okay, question 2. Sorry, I keep yawning. Find the theoretical probability. Now, theoretical means that no experiment has been done. We didn't actually roll any number dice here. We are just talking about the total number of faces of a die, and we're counting how many of them are called success. So if we're rolling a 2, and we want to know the probability of rolling a 2, there's only one spot on the number die that's successfully a 2, and there's 6 total faces. So the probability is 1 out of 6. Now I don't care if you want to make that 0.16 repeating, 0.167, those decimals are the same. Just show how you're doing it. You can leave the answer as a fraction. Now, could we ask more interesting questions than that? Sure we could. We could say, what's the probability of odd numbers? Well, there's 1, 3, and 5, so that's 3 successes out of a total of 6 choices. So that's 1 out of 2, or 0.5. What about prime numbers? Well, on a number die, remember a prime number has 2 factors. It has to have the number itself, and the only other factor would be a 1. So out of the numbers 1 through 6, we've got 2, 3, and 5 that fit that category. If you try to start arguing with me about the number 1, then I'll have to remind you that a prime number has 2 factors, and the number 1 does not have 2 factors. Therefore, it does not qualify as a prime number. So that's 3 numbers out of 6. Oh, doggone it, that's exactly the same as the last one, 0.5. And I did write down prime numbers have exactly 2 factors, the number itself and 1. Sorry, I didn't see that when I was spewing that information. Question 3. Among crossbred plants which can have purple or white flowers, and obtain 757 plants with white, 362 plants with purple. Find the experimental probability. Okay, so this is an experiment. This isn't just theory. They actually did the experiment. And so how many total plants are we dealing with here? Well, total plants, 1,119, when you add those 2 numbers together. So how many white flowered plants do we have? Well, we take the total number of white, which is 757, and we divide by 1119, and that's the 0.68, or 68%. If we take the 362, which is the other one, the purple, and divide by 1119, we get 0.32%. Now, over here on the side, I just thought I would ask this question. What happens when you add 0.68 and 0.32? You do get the whole number 1. And the number 1 goes with 100%, which makes sense because the only 2 options in our set of data were purple flowers and white flowers. There was nothing other than those 2 options, which is why it adds up to 100%. Okay, whoa, what did I write? Come on, come back to me. Oh, I use this example. Okay, I don't know what's going on with formative today. They've been kind of glitchy a little bit here today, so not sure if I'm going to get this to work. There we go. So you can't have white flowers and purple flowers at the same time. What this is illustrating is that these events are called mutually exclusive. It means they have no overlap. If I were to draw a Venn diagram of these, they would look like this. Nothing in common. Other standard Venn diagrams, which we'll see here in a future question, look like this, where they overlap. That is not mutually exclusive. I'll just abbreviate that with ME. This is definitely showing mutually exclusive, okay, because nothing's in common. Okay, the law of large numbers. We've had prisoners that have taken a coin and flipped it. We're talking like 10,000 to 20,000 times and recorded how many, the heads and tails, just to pass the time. And they have gotten real close to 50%. So the law of large numbers states that as you increase the number of trials, the experimental probability gets close to the theoretical probability. So what's the theoretical probability of rolling a 5 on a number die? Well, that'd be 1 out of 6. We talked about that before. That's 0.16 repeating as a decimal. We would expect when you're rolling a lot of dice that you're going to get close to this percentage for the probability of rolling a 5. It won't be exact when you're doing an experiment, but we're talking close. These events are mutually exclusive since you can't have two numbers roll it at the same time. Well, the class had number dies, and everybody kept rolling in the class and recording what they got. So we found out that the total that the class had of every time they rolled a 1, that happened 45 times. Rolled a 2, that was 46 times. Rolled a 3, that's 47, all the way through the 49. That, or let me see, 51, I forgot the end one. What do they add up to? How many total rolls did we have? Not the kind we like to eat, but the total rolls of the dice, 285 total rolls. Which means every single number of occurrences is going to get divided by 285. And when you do that, like 45 over 285 gives me 0.158. 46 over 285 gives me this one. 47 over 285 gives me that one, and so on. Notice how they're all close to 0.16 repeating. Definitely not perfect, right? We would have to do more rolls to see those numbers level out, and then the low ones would go higher and the high ones would go lower, and we'd get closer and closer to that magic number. On the next one, we have marbles, and we've got 10 red marbles and 60 yellow and 30 green. That's a total of 100. You first find the total. Then look at what they're asking me for. So we know that 100 is going to be in the bottom. What's the probability of getting red or green? Well, since these are mutually exclusive, that means there's no overlap. You can't reach in the bag and pull out one marble and it's got red and green on it. There's none of those kind of marbles in the entire bag. It's just a red or a green or a yellow. So these are mutually exclusive. And the probability of running or of pulling out a red or a green, well, you'd add the 10 and the 30 together. That's 40 out of 100 marbles. And you could leave your answer like that, or like that, or like that, or like that, or like that. I don't care whether you give me fraction, decimal, or percentage. Fraction, decimal, or percentage. Okay. Question 6. Once again, another marble situation, and we know that we need to find the total first. So we add up all the marble, or all of the blocks, not marbles, but blocks. There are 125 of them. So that's going to be my denominator. These are mutually exclusive events. You can't have one happening at the same time another is. And they want to know the probability of yellow or red. Since those are mutually exclusive, we just add them together, 24 plus 36, and that's how we get the 60. 60 out of 125 is 0.1 or 0.48. I asked a secondary question over here on the side. I said, what's the probability of not red or not green? Well, that would be purple and yellow, right? That's another way to say purple and yellow. And if I add the purple and the yellow, the 24 and the 19, those give me 43. And of course, the whole total is still 125. And so we get 0.344 as our final, or 34.44 if you like to write your answers as percentages. Nothing wrong with that either. Okay, on the next situation, it says that we have a group of 40 students from your school that's part of a television audience for a game show. The total number of people in the crowd is 130, so we're starting with 130. They're going to select so many people, 10 people, I think, 10 from the crowd. The question is, what's the probability that 4 students get selected from my school? Well, we're going to take the 130 and we're going to split it into 2 groups. First group is the kids in my school. The second group is everybody else. Does the order that the students are chosen in matter, or the people are chosen in matter? The answer is no. Therefore, we know we're dealing with combinations. First, we want to find the total groups of size 10. So, on the bottom here of my fraction, I've got 130 people, and I'm choosing groups of size 10. Now, that's a really big number, actually. It's in that I can type in my calculator. Now, on the top, this is where we split the groups into 2. So you can see on the left here, I've got my school students of 40, and on the right, I have the rest of the people of 90. Well, we're going to select 4 people from our group. That leaves 6 people from the other group. You can see that I drew an arrow from the 10, splitting it into the 4 and the 6 for the top. You can also see that I took the 130 and I split it into 40 for that group and 90 for this group. Now, those are all decently sized numbers, especially the denominator there. So I really think that it is extremely important that you use these parentheses on the top and the bottom. But let the calculator do the work. Just go straight to Desmos, just go straight to the calculator. Make sure you use parentheses around the things on the top and the thing on the bottom. And if you do, you'll get the 0.214, which is 21.4%. But that's what you will get. Okay. Last couple questions here. So we've got this, we've got a target, a round target, and we're going to throw a dart at it. Let's just pretend we're going to throw a dart at it. And somehow we're going to magically, there's no way I can miss the target. So I don't care if you want to imagine a long pipe that's being attached to the dartboard, and you throw it in the pipe, and it'll bounce around, hit the walls, and eventually it's going to stick into the dartboard. Unless, of course, you're just really skillful and you know what you're doing. Okay, but it's not going to miss the target. The question is it going to hit the red circle? Because, you are going to win a prize if you hit the red ring, that red ring. We do need to know the area of a form. So I have this really dumb expression that I use, pi r squarea. And the whole reason I do that is because the last four letters are area. So it's pi r squared. And you have that formula, which you probably already know, or at least should. Now, a long time ago, you had these kind of problems where you had two rectangles, one inside the other one, and then they would say, find the area of the shaded region. And so you would take the big rectangle minus the little rectangle. That's kind of what we're doing here for the numerator. So, first off, I need to know, where is my cursor for crying out freaking loud? Okay. Where is my area of that circle right there, which is got a diameter of 20? What's the area of that thing? Well, the radius would have to be 10. And since the radius is 10, that would be pi times 10 squared for the bottom, which is 100 pi. Okay. How about the little circle on the inside? Well, so we want to find the area of this circle right here. The radius here is 9. So how do I find the area of that? Well, that's where we do the pi times 9 squared. So that's 100 pi minus 81 pi on the top. That's where we get the 19 pi from. Then I'd ask you to think about what cancels out. The pi's cancel out. So we get down to 19 over 100, or 0.19, or 19%. Those are all good answers. So to find the ring, we have to subtract two circles, area of two circles. Now, let's go to the next one. The next one has the Venn diagram on it. So this is called a Venn diagram, V-E-N-N diagram. You notice that in purple I have circled the math, and in orange I circled the science. Now, it's nice that they have, filled in these circles for me. The 44 plus the 55, that's equal to 99. And the 55 plus 25, that's equal to 80. Well, guess what? Those match what they have right here. 99 are taking math, and 80 are taking science. You can see that they put the 55 in the middle where they have in common, where the students are that take both math and science. So over here I wrote down that the 44 number matches the taking math only, where the 55 is taking both math and science. The 25 is taking science only. Now notice down here in the corner there's a 29. It's outside of the math and science circles. Therefore, those people are not taking either. They're not taking either one. Well, if you add up all four of these numbers, you're going to get the total of 153 students. So we know that the denominator to our answer is going to be 153. Then they asked me this question: what's the probability of taking math, science, or both? Well, math only would be 44, both would be 55, 25 would be science only. That's a total of 124. We know the bottom is 153 because that's the total of the class. So when you divide those, you get 0.81. Some students have asked me today, hey, can I do that by subtracting the 29? In other words, the 29 are not what we are interested in. So if I take 153 and subtract the 29, that would find out everybody else that I am interested in, and I could divide that by 153 to get my probability. It does work, folks. Take away what you don't know. So I think that's the end of this section on 11.4.